So what we did last time, we wrote the Maxwell equations inside materials. It was the first time that we wrote the whole part of them without neglecting any terms, because we would be in vacuum or in the stationary case. And what we found, I don't know if Itai is back with us, but what we found is that we managed to write something that is not quite like a wave equation, but very similar, okay? And so the solution to this pseudo, it was a wave equation in complex notation, okay? Solution to this slightly modified complex wave equation was something we called pseudo waves, okay? And how did it look like? It was basically something that looked like a wave with a term, with a factor, okay, that was attenuating the actual wave, okay, an exponent that made it decrease inside the material, okay? And if you remember, we said, okay, there is these things should also be reflected. It should be reflected both in the shape of the wave and also if we look at the Poynting vector, okay, from the point of view of the material, and we saw that the maximum absorption of energy is actually in the same pulsation where we found the resonance. Okay, I didn't mention this, but we saw that there is some resonance effect at some specific pulsation that matches the pulsation of the I always forget how to say kvitz in English. Spring, yes. Okay, we derived this very simple classical model of the atom with an elastic link between the electron clouds and the nuclei, if you remember. And we saw that there is some resonance effects at the very specific pulsation that is characteristic of the material. Okay, and we saw that this resonance is visible in both the shape of the wave, okay? It's absorbed, the wave is absorbed, both the energy and the attenuation are maximal at this resonance. And of course, it's also visible from the point of view of the material because we have a resonance at this pulsation. And we will ask another question. Okay, we will ask a slightly different question, but we will take an approach that is a bit similar. Okay, we will ask what causes waves. Okay, and we will use, why am I saying that it's a slightly similar approach? Because we will use also a classical model that you and I know that it's oversimplistic because it's classical. In reality, we would need the entire arsenal of quantum mechanics in order to do things properly. Okay, so we already saw simple classical models. They do help us understand many things. So we will use a small a classical model, okay, to try to answer the question. And maybe you already have an answer, an intuitive answer from things you already studied before. Shall I? What is causing radiation? What is generating electromagnetic waves?
Moving
electrons.
particles.
Okay, so I'm hearing moving particles. I heard something else, but I wasn't able to.
Movement of electrons.
Movement of electrons, and it's even so. Yes, but it's even more than this. It's actually acceleration of electrons. Okay, it's not enough that they move, we need them to accelerate. Okay. So, okay, so did you derive the radiating dipole in any of the courses before? Did you do the full derivation? Okay, I'm hearing silence, so I'm guessing no. Okay, so what we will do now is that we will do a full derivation. We will do a bit like last time. I will give you the ingredients of the model, of this classical model, and then we will make the full derivation of how from this very simple model I get to an electromagnetic wave, okay? And I'm warning you that this derivation is pretty technical, so you have to stay tuned with our derivation. And then at the end of the first part of the course, I will try not to make it longer because of the first part that we are doing now is going to be just a rigorous and technical derivation of how we go from a single model to from a simple classical model to electromagnetic wave. Okay, what are the ingredients of this model? They are the following. So we have a dipole, okay? We mentioned that we need some moving particles in order to generate radiation. What we actually need is an accelerating particles within a dipole. Okay? It's not enough to just have one particle. So first ingredients is a dipole. Okay, so let's draw it. So we have one particle here and another one here, which is minus t, okay? And the distance here is d. Here I have O, okay? And here I have my negative and my positive charge, okay? And the way I'm going to formalize the movement is the following way. The charge Q of t is equal to Q0 cosinus omega t, okay? Okay, now what does this mean? It can mean you can have several mental picture on what it means. They are all equivalent, but we're going to use one because it's going to make it easier to derive the rest. Okay, so what we imagine is that we have two charged balls with a wire in between, okay? And the charges are going back and forward. There is actually a current in the string that allows some movement of charges between these two charged balls. And the way they move, the way the current is working is ensuring that Q is always opposite to minus Q, okay? The charges of the balls are always opposite. Okay, there would be another way to imagine this. We could imagine two charged balls which are not linked by a string, and the distance between them is changing. Okay, I'll show you in a minute that this would be equivalent, but this is not the picture we're choosing. Okay, we're choosing some fixed charged spheres with charges moving in between in a way that is symmetric. Okay, and the result of this is that we have a variable dipole moment. Okay. So we have P of t, which is going to be Q and P. Okay, this is the way we always write things. Okay, so this is going to be Q0 cosinus omega t d ez. Okay, I have a small unitary vector here, ez. Okay, and this is equal to P0 cosinus omega t ez. Okay, and you see that I could have the exact same results, okay, this varying dipole moment, if NP was the part, if Q was fixed and NP was the part that was oscillating, right? This is just what I just mentioned, that we would reach the same result, but it will make it harder to derive things later. So this is the mental picture that we choose. Okay, so I'm gonna go into in a minute into the detail of the derivation, but I'm already telling you that another very important ingredient in this model is 3 consecutive approximations, which we will be doing. Okay, I will detail them in a second. And the last ingredient is a concept that we will need to accept, okay, which is called retarded potential, and I will retarded potential concept. Okay, so I will explain in a minute. Okay, but let's before I go into the details of 2 and 3, let's draw the configuration we will use. It should remind you of what we did with the dipole in the stationary case. So we have here O and P. Okay, I need this more detailed configuration to explain all the approximation I'm doing. Okay, so this is similar to the dipole you already know. I have theta here. Here I have R plus. Here I have R minus Q plus Q. Okay, and here I have something that I'm calling R. Okay, this is equal to OM. Okay. Okay. Now, what did we do? You probably remember in the dipole case, we used the cosinus, משפט הקוסינוס, the cosinus theorem, right? And we used the following, right? We also wrote, so this was equal to d over 2 square plus r square minus 2d divided by 2 r cosinus theta. Okay, we did the same for r minus, and we derived the following, that r plus or r minus is equal to square root of r square minus plus dr cosinus theta plus d over 2 square. Okay, and of course we will do, we will neglect terms, etc. But this, I would say, is the basic configuration that we have. And I'm also reminding you what we got in the static case, okay? Static case, we got the following, that V of M, the potential at this point here, okay, was equal to Q over 4 pi epsilon 0 R plus minus Q over 4 pi epsilon 0 R minus, okay? And then we developed R plus and R minus, correct? And we neglected all kind of terms, and we went from this to the dipole approximation, okay? To the multipolar development, okay? Now, there will be now 2 things that are very different from the static case, and battery is low. Let me just get... okay, so there will be 2 things here that are different from the static case, okay? The first thing is that Q is changing with time. Okay, so 2 differences from the static case. Difference number 1 is that Q is varying. Okay, and the second difference, and this is what brings me to this concept of retarded potential, is that in our case, I need to somehow take into account, okay, because I'm talking about an electromagnetic wave, I will take into account the fact that it takes time for the information to go from this area to this area, okay? Okay, so if you remember in the static case, we said, we don't mind about the time it takes. We are also looking at stationary, at equilibrium states, okay? We're not looking at this transitionary phase where something is happening here at the dipole location and not well established yet at the location of M, at the location of the point where I'm asking what's the potential. And here, okay, here we take into account the propagations times. Okay, but it's important to understand that there is a distinction between these two, okay? They are not quite the same and they are both going to influence our derivation, okay?
מה כתוב באחד? Q is what?
Q is varying. Okay? But my point is that this alone is not enough to make all our derivation, okay? We have these two aspects are important ingredients in our derivation. Okay, so now let's go into more details. So in the static, I'm going to make here two columns, case, and here electromagnetic wave, case. Okay, so at the time, I had the following. Okay, I had some integral on the distribution of, let's say it's a volume one, rho n d tau, 4 pi epsilon 0 and n. Okay, and if I looked at the vector potential, I had mu 0, j n d tau. We also wrote this as did C, okay, the current element, okay, 4 pi nm, okay. Now it's going to be slightly different. I'm going to allow the potential, both of the potential to change with times. Okay, and V this time is going to be rho n tr. I'm going to say in a second and you can start guessing what is tr. 4 pi epsilon 0 and m. Okay. And so what is going to be the expression of tr?
The time it take, like the t plus the time it would take for light to reach from the location from N to M.
Right. So t actually minus the right? Okay. So Itai is talking, right?
Yeah.
Okay. So what Itai is saying, and this is indeed the answer, the potential at the point M, okay, is going to be equal to the potential at N, okay, so the potential here is going to be equal to the potential here, okay, at the dipole when at t before the time it took to the information to travel between the dipole and the point M. Okay, and here I'm making a strong assumption. What did I assume here by using C? I assume that whatever is traveling, the information, the light, the wave, is traveling at a velocity c, okay? And this is something that I'm assuming, okay? I'm using it, I'm assuming it, and I'm definitely not proving it, but we saw that when electromagnetic waves were discovered, people realized that they were similar to lights, okay, so this velocity.
I mean, you can't prove it with the Lorentz gauge. You get a wave equation.
Sorry?
But you can prove it with the Lorentz gauge.
Okay, exactly. So in order to prove it, we would actually have to show that these two potential that I wrote, okay, VMT and AMT, this is what we call the retarded potential. So these two things here are what I'm calling the retarded potentials. Okay, so in fact, I would have to show that A and V are solutions of the wave equations, okay? And this is actually equivalent to showing that there are solutions, that these two expressions of V and A are indeed solutions of the Maxwell equations, right? It's equivalent because I'm deriving the wave equation from Maxwell. Okay, but so this is something that I'm not going to do now in detail. I'm going to use it, okay? So this was the third ingredients in my, okay, so I used this ingredient here, okay? And now let's start, let's go into the derivation and use these three approximations that I mentioned. Okay, so I have that VMT, okay, if I'm trying now to write something similar as the expression of V in the static case, okay? So I'm going to do the same thing. I'm going to open a V, okay? And do approximation. So VMT is going to be equal to 1 divided by 4 pi epsilon 0, Q0 cosinus omega T minus R plus C, okay, divided by R plus minus Q0 cosinus omega T minus R minus C, divided by R minus, okay? Where R plus and minus is equal, like in the static case, to R square minus plus dr cosinus theta plus d over 2 square. Okay, and this is also R 1 minus plus d divided by R cosinus theta plus d over 2R square. Okay, and this is very important. I will use it over and over. Okay, but make sure that you agree that this is just the equivalent of writing this in the static case. Okay? Good. So let's start now with our approximations. The first approximation we're doing is the one you already know from the static case. So approximation number 1. So what is the standard approximation that you remember from the static case? And it helped us simplify both of these expressions.
Small angle?
No, so you remember that in the static case, we didn't keep these two expressions, right? Very quickly, we neglected this term, the D over R term, right? Okay, so approximation number 1 is to assume that D is much smaller than R, okay? And this has as a direct implication that R plus minus is equal to, I'm actually doing a first order expansion of this thing, okay? So it's going to be R1 minus plus T over 2R cosinus theta. Okay, so I'm basically neglecting here the last term. And if I do it, okay, eventually you see that in the expression of the potential here, you see where I'm pointing? It's a pity that I cannot show you on the screen. But you see that what I need is not it's not R plus minus, it's 1 over R plus minus, right? So I'm going to do a second development, and it's going to be 1 over R, 1 plus minus D over 2R cosinus theta. Right? You agree? Everybody agree? Who doesn't agree? I hope you agree. They will lose track because we're just in the beginning. Okay. Okay, so this is the first approximation I did. I've reached the bottom of the page, so let's start a new page. Why do I have this here? Okay, I started a new page. Okay, so I'm gonna use now so what I have in my, let's quickly rewrite the potential so that I have it handy. Okay, so I have that V mt is 1 over 4 pi epsilon 0 Q0 cosinus omega t minus R plus divided by C minus Q0 cosinus omega t minus R minus C. Okay. Okay, and I just wrote expressions for R plus minus. Okay, so omega of t minus R plus minus C is going to be equal. I now want to develop these things. So it's going to be equal to omega t minus omega over C R minus plus half of the cosinus theta. Okay, and cosinus of this. Okay, until now I'm just doing the exact same thing as in the statical case, but because I have these cosinus shapes and this time dependence, I need to work a bit harder in the development. Okay, so omega of t minus R divided by C plus minus omega d to C cosinus theta. Okay. Now I'm going to use now trigonometric identities, and I'm going to open this cosinus. Okay. So I'm going to use that cosinus of A plus B is equal to cos A cos B minus sin A sin B. Okay, so I'm getting that this is cosinus of omega. You should really check that you agree in real time. Okay, cosinus of omega d to C cosinus theta, right? I have the cos of a cos, cosinus of a cosinus, right? Minus plus sinus of omega t minus R over C, sinus of omega d to C cosinus theta. Okay, here I have the cosinus of the sinus of a cosinus. Okay, right? And I'm going to call this term B and this term A, okay? Gonna help me in the drawing. Okay, so the second approximation that I'm doing, okay, in the static case, we only did one approximation and it allowed us to derive everything. Now it's not going to be enough. So the second approximation I'm doing is the following. I'm assuming that D is much smaller than C over omega. Okay? Now, let's reflect on the meaning of this approximation. What does it mean? So I remind you that omega, the pulsation, is 2 pi nu, right? Where nu is the frequency, right? And lambda is C over nu, right? So C over omega is equal to lambda over 2p, okay? And so assuming that D is much smaller than C over omega, it's actually equivalent to assuming what? That D is much smaller than lambda. Okay? So for the moment, the lambda here is only some formal lambda that is related to the pulsation of the dipole. Okay, but what we will see later, and you can already guess this, is that this dipole is going to emit a wave with a wavelength lambda. Okay, the pulsation at which my dipole is vibrating is actually going to be the pulsation of the electromagnetic wave it emits. We haven't proven it, but we can already guess this. Okay, and if we accept this approximation means that the wavelength of the radiation that is emitted is much larger than what? What is D? D, if you remember, I'm going back, is the size of the dipole. Okay? So making this approximation is simply saying that the radiated lambda is we haven't showed it, not shown yet. Okay, is much larger than the size of the dipole. Okay, and in real life, okay, the dipoles that we're talking about are actually molecules or, I mean, small particles at the molecular scales, okay? And the lambda we're talking about, the emitted radiation as wavelengths that are indeed much larger than the, okay? So let's make a small back of the envelope equation. So molecules, what is the size of the atom? This is something we should know at the end of a physics degree. Okay, it's about 10 to the minus 11 meters, right? And visible light, this is about 10 to the minus 7 meter, right? 0 point something micrometers. So this is actually happening. We know it's happening in the real world, okay? And this is already an indication that this model will help us explain the real world because the approximations that we need in this model are indeed met in the real world, okay? We're not doing some approximation that is never going to be met. This approximation is met, so we're in good shape to use this model as a simplistic picture of reality, okay? Okay, so let's continue. So we have here A and B, and we want to simplify them. We want now to simplify this, okay? So you remember that cosinus x is equal, if I develop, I don't know if you remember the development of cosinus and sinus, so I will remind it to you. So cosinus x is this, okay, plus, actually this is a minus, okay, all the higher orders. And sinus x, do you remember? A development for the sine. What does it start with? So when x is small, I can
X, 0.
Right. So when x is small, sine is actually close to x, right? So this is the first terms of the development. Okay, so this means that A is, like, can be approximated by 1, okay, and B, these are A and B from the derivation above. So B is approximately what?
X.
Right, but in our case, it's about omega D over 2C cosinus theta, right? You agree? It's this B, right? Okay, I'm talking about A and B in this expression. Okay, so this means that I'm going to be able, so I had this here expression of the potential that I want to simplify. Okay, I remind you that this is my motivation the entire time. I want to write the potential and I want to simplify it. And as opposed to the static case, it's harder to simplify that in the static case, but I can simplify it with this. Okay, so the expression I had here for this thing, okay, I can rewrite it with this approximation, okay, and write that cosinus omega t minus r plus minus over c is equal to cosinus omega t minus r over c times 1, okay, a is 1, minus plus omega over c cosinus theta, this is b, right? Sinus omega t minus r over c. Okay? And so let's put this in the, okay, I've rewritten this. Let's put this in this first equation here where I wrote my potential. And I want to check how long I need to reach before the okay, so let's put this in the expression of the potential. So let's do it together. Try to do it together because it's going to highly facilitate understanding this at home, and we can definitely ask you something similar in the exam. Oh, what did I do? Okay, come back. So the potential is Q0 over R. Okay. 1 plus d over 2r cosinus theta. Okay, this I had already. And now I have I'm putting this in the potential, okay? So I have cosinus omega t minus r over c minus omega t cos theta sinus of omega t minus alpha t. Okay, so this is the first term with R plus. And I also have a second term. Minus, minus Q0 over R. 1 minus D over 2R cos theta. Cosinus omega t minus C plus omega t C cosinus theta sinus omega t minus alpha. Okay, so these are the two terms I had. Okay, and it's still not the most friendly expression. Okay, this I want to give it a name because I don't want to have to rewrite it every time. So let's call it. How should we call it? I already had. Let's call it C. Okay. So let's write it. I'm continuing the development. So I get 1 over 4 pi epsilon 0, Q0 over R plus P0 cosinus theta over 2R, right? Cosinus C minus omega D to C, cosinus theta sinus C, okay? Minus Q0 over R minus Q0 P cos theta. I told you it's a bit technical, this part. Okay. And here I have cosinus C plus omega D over 2C cosinus theta sinus. Okay. Now, if you open this expression, you can already see that there are a lot of things that cancel. And please try to do it, but let's open it. Okay, so it's going to be 450 Q0 over R cosinus C. You see that this is coming from here, and it will cancel out with these terms, right? Minus Q0 omega D R 2C cosinus theta sinus C plus, okay, 2R minus P0 cos theta omega D 2C cos theta sinus C. Okay. And now when I'm developing the second part, I have these terms that cancel, right? Minus Q0 omega D R to C cosinus theta sinus C plus P0 cos theta cosinus C over 2R plus P0 cos theta and omega D C cos theta sin C, and this cancel with this. Okay, so this was a bit tedious. So I can get the P0 cos theta out of the this, okay? and get the following: minus omega 2c sinus c times 2. I have 2 of these terms, okay, plus 2 cosinus, cosinus c over 2r, okay? And so if I summarize everything, I'm going to get the following expression: V r theta v is equal to P0. Let's write it on the next page. Okay, so I have that V r theta t is equal to P0 cosinus theta over 4 pi epsilon 0 r minus omega over c sinus omega t minus r over c plus 1 over r cosinus omega t minus r over c, and make sure we reach the same expression, okay? So this is the simplified expression for my potential. Okay, I'm going to call it, going to put here way asterisk. Okay. And before we do a third approximation that will help us write this in an even simpler way, okay, this is not good enough yet for what we want. I remind you that what we want is to show that the potential is going to have the shape of a wave. And it's not quite good yet, but before we add another approximation, let's think about the physics meaning of this. So if I bring the pulsation to 0, this is actually the static limit, right? Okay, and then V goes to P0 cos theta 4 pi epsilon 0 r squared. Do you agree with this? You should agree. Okay, and this is a stationary dipole. Okay, so we're happy because
I don't think we see your screen now, מעיין. Like frozen. Maybe it's just for me.
and what's the last thing that you see?
I see a blank page.
Is everybody in the same?
No, okay, so it's just me.
So
Maybe it's my internet.
okay, so for the other people, what is the last thing you see?
The potential.
The stationary one?
The stationary dipole potential.
Okay. So Yuval, I hope it will be solved soon. Okay, so you agree when you bring in this expression of V the omega to 0, we are back to and we're up. Okay, but it's not quite enough yet, as I said. And the third approximation that we're doing, and we will end this with this and take a quick break. Approximation number 3 would be to say that R is much larger than C over omega. Okay. Now let's reflect on the meaning of this approximation. So as I said before, lambda, we want to compare things to lambda, okay? So lambda is equal to C2P over omega, right? So if I assume that R is much larger than C over omega, it's like assuming what? that R is much bigger than lambda, right? So if I summarize things, approximation number 2 was to say that D is much smaller than lambda. Now R is much bigger than lambda. So if we summarize of approximations 2 and 3, I'm actually assuming that D, the size of my dipole, is much smaller than the radiated wavelength, which itself is much smaller than the dimensions on which I'm basically phrasing my problem, okay? I'm looking at the value of the potential at a much larger distance than the wavelengths of visible light, okay? Okay, now let's look at what this will do to my potential. So if R is much larger than C over omega, of course, 1 over R is much larger than C. And so this, okay, I'm putting these asterisks because you're not seeing me, so you're not seeing where I'm pointing. So these 3 asterisks are the expression of the potential, okay? So this will become what? VR theta T is going to be equal to minus 0, 4, 5, 0, C, cosinus theta over. Okay. Sinus omega T minus R over C. Okay. Why? Because this, let's look at the potential, okay, I have here 2 terms, right? And if omega C is much larger than 1 over R, then the first term of this potential is much larger than the second term, okay? Cosinus and sinus, I know they're within minus 1, 1, okay? So, but the factor, I can compare the factors and neglect the second term compared to the first term, okay? So I've reached a much, much easier expression of the potential V, okay? Okay, now let's take a short break. Yes, let's maybe try to make it better than usually so that we have time without delaying to the lecture. So let's resume. Is that okay? Raise your hand if you have an objection. No objection? Okay, so let's be back at 9:45 and hoping that the technical gods will still be with us. Okay, so see you in a bit. resume. Okay, so I'll tell you what I want to reach in these 40 minutes. So we've derived a simplified version of the potential emitted by a dipole, right? A moving dipole where we derived the simplified version of the potential emitted by a moving dipole, and now we will want to do the following. We will want to derive the vector potential. Okay, this was just the electric potential. So we will want to derive the vector potential A, and then we will want to derive the fields, right? Eventually, we want to ask what are the fields emitted by this dipole. Okay, so this will take us about 15-20 minutes of more of hardcore-ish derivations. And then we will take one step back and really try to extract the physical meaning from the shape that we will have derived for both the fields and the potential. And in the last few minutes, we will see how this very simple model actually helps us understand very basic stuff from our everyday experience. For example, the reason the sky is blue, right? Okay, so let's continue from where we stopped, and now we want to do the same. We want to derive the vector potential A. Okay, and for this, we're going to take a similar approach than we did. So for this, we need to remember that DC that goes into the, so if you remember, let's go back to the first page. Okay, so the vector potential is here. Do you see my screen? You see my screen?
Yes.
Okay, so I have the vector potential here. Okay, and the key here is to remember how to write DC, the current element. Okay, so DC, if you remember, is equal to I dz. Easy. Okay, this is what we have in the case of a string. This is the way we wrote the vector potential in the Biot-Savart expression of B. Okay, this is how we wrote this part of the fraction. Okay, so plus Q minus Q. Okay. Now I have a small dz here. Okay, here I have theta, and here I'm writing it as a round R. Okay, and so DC is equal to okay, so I is equal to what? To dq over dt, right? And this I know how to write, right? Because I know the expression of Q. So this is minus Q0 omega sinus omega t Ez dz, right? Potential as the following: mu 0 divided by 4 pi. And here I'm integrating between minus half of d to half of d. minus Q0 omega sinus omega T minus R over C did Z divided, this is this round R, easy, okay? Where R is equal to what? It's equal to R square minus dr cosinus theta plus d, sorry, this is Z, so I don't know how to erase things on this. Okay, so I'm just gonna do it the old way. Z2 square, okay, so make sure you agree. Okay, and so 1 over round R is equal to 1 over R, 1 plus Z over 2R cosinus theta. Okay. Okay. And so if I rewrite this, I have that A T is equal to minus mu 0 4 pi. It's a vector, of course. 4 pi Q0. So this term, I will actually neglect. If I neglect this, I will neglect it later, actually. For now, I don't neglect it, but if I take things out of the integral, I'm getting the following, EZ integral of dz over R. Okay? So I actually had to work less for the potential. So the vector potential of R, theta, and T is equal to minus mu 0 4 pi R P0 omega sinus omega T minus R over C EZ. Okay? So this is the expression of the vector potential. It was easier than for V. And now we want to calculate, we want E and B. So how are we going to derive E and B? Let's start with E. Start with E. So we have A, we have a V, okay? And we know that E is equal to what? How do I write E as a function of V and A? This by now you should know. I hear silence. So I hope you know it. So this is minus grad V minus dA over dt, okay? So I can simply do this. Now that I have an expression for V and A, I can simply develop this. Okay, so let's start. So let's start by we'll start by calculating this and then this. So let's calculate grads of V. Okay, so I'm in cylindrical coordinate, right? So grad of V is V did V dr ER plus 1 over R did V d theta E theta, right? And this
0c. This is cos theta. Okay, I'm just doing the derivative. Sinus omega t minus r over c minus omega over rc cosinus omega t minus r over c. This is with an ER, right? So this is just the first term here. And here I have another term, which is sin theta over r squared, sinus of omega t minus r over c, e theta. Okay? And I remind you that approximation number 3 was to say that r is much bigger than c over omega. Okay, so 1 over r is much smaller than omega over c. And so I'm able to neglect, so this term here is going to be much smaller than this term here, right? If I call this A, so we can keep A only, right? Because the factors in front of the cosinus and sinus allow me to do this with this approximation. Okay, so as a summary, I have that grad of V is equal to P0 omega square, 4 pi epsilon 0 C square, cosinus theta over R, omega T, of cosinus of omega T minus R over C, ER. Okay? But this is only one of the terms I need to derive the field, right? It's not enough. I also need the vector potential. So now, this was 1, this was 2. So let's calculate dA over dt. Okay, and this I will let you do. Okay. Exercise. Okay, and you will get that the answer is that dA over dt is equal to minus mu 0 p0 omega square 4 pi r cosinus. I have a cosinus here of the usual thing, and then here I have cosinus theta ER minus sin theta E theta. Okay. And now I need to use both 1 and 2, okay? Because E is minus grad V minus dA over dt. Okay? E is minus grad V minus dA over dt. Right? So here again, so here there is a trick. But this I will also give you as an exercise. It's 2 lines of calculations, and you will get that E is equal to mu 0 P0 omega square divided by 4 pi sin theta R cosinus omega t minus R over C E theta. Okay? This is a very important way to write the E, and we will get a lot of meaning from this in a second. Okay, but let's before we take one step back and reflect on the meaning of this expression for the field, let's derive the magnetic field too. So how do I write B as a function of the potential, the vector potential A? What shall I do now? I have A. How do I write B? Oh, this you should really, really know.
Curl.
Yes, thank you. So B is root of A, okay? And root in cylindrical is the following. R A theta minus D A R D theta E phi, okay? And A, we showed, is equal to something like this. With a sign here. And here a cos theta ER minus sin theta E theta. Okay, so do it as an exercise and show that root of A is equal to minus mu 0 p 0 omega 4 pi r omega over c sin theta cos omega t minus r over c plus sin theta over r sin of the same omega t minus r over c e phi. Okay? And here again, I'm using approximation number 3. Okay, that tells me that R is much bigger than C over omega. And so I can simplify this and keep only what? I can keep only this term, right? Do you agree? Who doesn't agree? Right? Because R is much larger than C over omega, 1 over R is much smaller than omega over C. And so the second, this expression is completely dominated by the first term. So we can keep only the first part, this part. Okay, so if I summarize, B is equal to minus mu 0 p 0 omega square 4 pi c sinus theta over r cosinus of omega t minus rc e phi. Okay? Okay, now for all of those who lost track a bit because of all the calculations we did, this is a good time to be back with us, because what I will do now is to take one step back and examine these two expressions for E and B. Okay, I remind you that what we did, we started with this very simple model. Okay, we made a few simple assumptions on the configuration of the dipole, on how things are located in space, okay? And then we added 2 ingredients to this model. First ingredient was the very concept of retarded potential, okay? The fact that I need some time for the information to propagate between the area where the dipole is and the area where I'm standing, okay? And we made 3 approximations. And in the last hour and a half, we worked pretty hard, okay, to derive these 2 expressions for E and B. Okay, we started by deriving the potential B, the potential V, then the vector potential, then we used the definition of this potential. We derived these 2 expressions for E and B. This is what we wanted, okay? Now I'm taking one step back and I want to with how the most meaning from these two expressions of E and B. Okay, so let's do it. So first, let's look at this expression. So we started, what was omega? What is omega in our model? Omega is the pulsation of the dipole, right? And if you look, do you see that these two squares, E and B? I want you to look at them straight in the eyes. So we see that here, E and B are pulsating too, with a pulsation omega, right? So this is what I mentioned before, that before we hadn't showed it, but now we have showed it. We have showed that if I have a dipole that pulsates at a given pulsation omega, okay, it will generate some fields that themselves pulsate at this pulsation. This is not obvious, right? It could be omega times something. It's not obvious, but we've now showed it, okay? That a dipole that oscillates with a pulsation omega generates a monochromatic wave with pulsation omega. 1 second, I will just close the door. Okay, now, so physical meaning of E and B. Okay, so we have many. So first thing is that we have a monochromatic. You remember that when we talked about waves and we asked what is a wave, we said that any function where the space and time dependency will be of the shape of T minus R over C or R over V. We said that this is the very definition of a wave, right? Do you remember this? So first thing, this dependency here, this dependency is telling us we have waves, okay? And with the pulsation of this wave, of this monochromatic wave is the dipole pulsation. Okay, not obvious, but we're happy this is the case. Okay, so okay, I have a new page.
יש מצב התולה רגע למעלה?
מה?
יש מצב התולה לשנייה?
מי מדבר על זה? מה זה אומר?
לעלות חזרה למה שכתב.
לא, אז אי אפשר לעלות, כי זה דף חדש, אז מה שאני אעשה זה שאני עכשיו מתחילה דף חדש, אני אעתיק שנייה את E ו-B, בשביל שיהיה לנו את זה מול העיניים, ואז אני אכתוב שוב משהו כמעט זה, בסדר? סינוס תטא over R, קוסינוס אומגה T minus R over C, E theta. This was E, and B is equal to minus mu 0 P0 omega square 4 pi C sinus theta over R. Okay, so these are the two expressions we worked very hard to derive, okay? And now I'm writing the conclusions, the physical conclusions of these expressions of E and B. Okay, so first conclusion, we're dealing with waves. We have waves. Okay, and this is why, how do I see this? This I see, we see this from the dependency, this from the time space dependency of E and B, right? We saw that any function that looks like this with this kind of dependency is actually a wave, okay? Second, these are monochromatic waves. Waves that have the same pulsation omega as the dipole, okay? And this is not obvious. I mean, it's obvious to us, but it just comes from the calculation. Okay, third conclusion, still from the dependency, from this dependency here, okay? You can tell me how fast these waves travel, right? How fast do they travel? Remember, we spoke about the fact that for a wave that travels at velocity v, the time dependency is t minus r over v, right? So from this time dependency, I see that these waves travel at the speed of light. Okay, now here I'm cheating a bit. Why am I cheating a bit? Because when I assumed that there is such a thing as a retarded potential, I actually introduced this T minus R over C in the equations, okay? So I actually assumed this. So it's not really a conclusion. Speed of light. It's not really a conclusion because I made an assumption to reach this, but in any case, they travel at the same velocity as the velocity I assumed for the retarded potential. This is the important point. Okay. Okay. Second, fourth conclusion, these fields are in phase or not in phase, E and B? If I look now at the structure of the wave, E and B are in phase. Do you agree? I don't have any phase difference. E and B are in phase. Now, this too is not obvious. If you remember, when we derived the last time the waves inside materials, E and B were not in phase, okay? Still, if I talk about the structure of the wave, how are E and B located according to each other?
Orthogonals.
Yes. E is orthogonal to B, and they are both transverse, okay? They are both orthogonal to EZ, to the direction of the propagation, right?
Oh, what about the magnitudes? Aren't they supposed to be different?
We'll talk about the magnitude in a second. Actually, we can talk about it now. So E0 divided by 0, B0 is equal to what? Let's do it. I'm going to neglect this sign for a second, but it's mu 0 P0 omega squared divided by 4 pi divided by mu 0 P0 omega squared divided by 4 pi C. Okay, this is C. So actually, E0 is equal to CB0. This is exactly what we had when we derived electromagnetic wave propagation in vacuum, right? Actually, all of these things are exactly what we expect for electromagnetic propagation in vacuum. Okay, this was 2 lectures ago. We showed that when I have an electromagnetic wave in vacuum that I derive from the Maxwell equation, I'm getting exactly this structure. I spent like half an hour or 1 hour talking about the structure of the electromagnetic wave in vacuum. This is exactly what we get, right? Right, we had in vacuum, we had that E. Actually, I can summarize 4, 5, and 6 can be summarized as E plus C0 EZ cross B equal to 0, which is exactly what I had in vacuum. Okay, now let's still nuance this a bit. Okay, we need a bit of nuance. These 2 expressions are only true within the 3 approximations that I did, right? Which actually mean, physically speaking, what do they mean, these approximations? They mean that I'm standing very far from the dipole, okay? So let's make a comment. All this true within the approximations we did, okay, which are the following, okay? So I'm standing far, the size of my dipole is much smaller than the pulsation of than lambda, which is linked to the pulsation of the dipole, and okay, and I'm standing very far from the dipole, and
מה כתוב בביטוי לפני ה-EZ? בצד השמאלי של הרוטום?
פה C0, C.
סבבה, כאילו המהירות בוואקום.
כן, מהירות האור בוואקום. כן. זה C, שמתי פה 0, אבל אפשר לראות את C פשוט. בסדר? אוקיי. Now, I have some more comments. Okay, so there is something, it's true that there are very similarities with what we already saw, but there is also something new, which is this thing, right? In all the wave shapes that we saw until now, we didn't have the entire time and space dependency was in this T minus R over C or R over V term. We didn't have some more space dependency in the amplitude, and this is the case here. So this is telling me 2 things. This sinus theta over R terms is telling us 2 things. So first thing, this wave is going to be decreasing when R grows, right? So it's actually, I can say it already. So amplitude decreases when R grows, okay? This is one thing. And the other thing is that I have what we call an anisotropy, okay? So anisotropy of the amplitudes, okay? The amplitude is not going to be the same in all directions, right? Because I have this angular, this sine theta dependency, right? So it's going to be 0 in the direction of the dipole, right? When we are aligned with the dipole, I will have no wave at all in direction of dipole, and it's going to be maximal when we are perpendicular to the dipole, right? right? And this is actually a characteristic of spherical waves. Okay, so this is a very important point. And the last point I want to make, is that the amplitude, it's still about the amplitude. The amplitude is proportional. I will show it in a second. Proportional to the second derivative, the second time derivative. Are you know this notation with two dots? The second time derivative of the dipole moments. Okay, so let's show it. Okay, we have that P of t is equal to P0 cosinus omega t, right? So P dot is equal to minus P0 omega sinus omega t, and P with two dots is equal to minus P0 omega square cosinus omega t, right? And if we look at the the way we wrote E and B, this is indeed the case, right? I have here this minus P0 omega square with the cosinus. Okay, so actually in the expression I have for E and B, the cosinus is not quite omega t, it's omega t minus R over C, but I can definitely write that E is almost, 1 second. So E is mu 0 over 4 pi sinus theta over R, P of t minus R over C, E theta. Okay, and why is this interesting? Because we said in the very beginning, I asked you what are the things that generate electromagnetic wave, and you said it's a movement of particle, and I said not only a movement, an acceleration, right? And P, okay, is actually, so if we had in the model that we looked at, we didn't have our spheres of charge were not moving, right? But I said that it would be equivalent to to imagine charge that are moving, the distance between them is changing with time, okay? And so in this case, P would have been proportional to the distance between them. Actually, it's not L, it's D, right? The second derivative of the distance between them, and this is exactly an acceleration, right? So this brings us to the original intuition that you said, right? That waves are generated by acceleration. So we see here that indeed the fields, the electromagnetic fields are actually, their amplitude is proportional to the acceleration. That waves are generated by acceleration of particles. Okay? Okay, so these are all the conclusions I wanted to draw from this model, the physical conclusions. This model is super important. It allows us to explain tons of things. I will say I will spend 5 minutes. I might finish at 10:35 so that I have time for this, but we see that very simple, not simple, they're not simple at all, but they're very common experiences of our everyday life can be explained with this very simple model. And antennas, for example, we will have exercises about antennas. So to model antennas, we're just modeling many of these dipoles that I started with, right? And so this is how antennas are radiating, right? if you model an antenna as just an accumulation of many of these dipoles, you get the explanation of how do antenna radiate emissions. So I will end with a quick derivation of why is the sky blue. Okay, this will be like an illustration of how important this model is. Do you have an answer to this?
I know the answer as a name of a term, but not the definitions.
Okay, so this will be the last thing that we'll do in the lecture and in the course. Okay, so let's do the derivation quickly. In order to derive this, we need to look at the energetics. Okay, let's look at the Poynting vector we get from E and B. Okay, so P is equal to E cross B divided by mu 0. Okay, and if you replace, so if we replace with the value E and B that we derived, okay, I let you do this. What you get, so this is also equal to E0 C0 E square ER, easy, right? So if you derive with, you can, okay, you can replace here with the expression we got from for E, okay, this one. And so if we replace, we get that P is equal to mu 0 P0 square omega to the 4 C 16 P square. And here we have a square of a sine, a square of R, cosinus square of something that I'm not going to write because it's actually ER, it's not ER. It's not easy, okay? This is very important. It's ER. It's in the direction of the cylindrical ER. Easy is the dipole direction. Okay, so
מה כתוב במכנה בהתחלה? C מה?
C16.
Okay, thank you.
Okay. So this you can show, but it's maybe 2 lines of calculations. Okay, I'm not doing them. We did a lot of calculations today, and I want to reach the bottom line. But this is the expression you get for the Poynting vector. Okay. Now it's important to realize that in the visible, omega is in terahertz. Okay, and it's very, very hard to actually measure the instantaneous value of the energy of the Poynting vector. Rather, what we do is what we're more sensitive to, what is more measurable, is the mean value of the Poynting vector. Okay, which is equal to mu 0 P0 square omega 4 32 P square C. Okay, sinus square theta R square ER. Okay. So first, if we look at the shape of these things, okay, it's actually, we have the same as the anisotropy as before, right? And if we look at the shape of this thing, it's actually, see if I manage to. So the Poynting vector structure, it's like a donut. Okay, This is how it looks like. So it's maximal in the equatorial plane, right? Okay. Now, so this is the mean value of the Poynting vector, and if we calculate now, so you remember that the Poynting vector is a flux of a power, right? It's energy. It's like a current of a power, right? When we derived the meaning of the Poynting vector, okay, it's a movement of power, of energy per unit of time. So if I want to calculate the mean power of the electromagnetic field through a given surface, okay, I have to integrate the mean value of the Poynting vector through this surface, okay? And this is simply mu 0 p0 square and 2c p2 f4. So f, okay, omega is 2pf. F is nu, okay? Okay, this is the frequency. It's just easier to remember. Okay, and here I have an integral of a surface element, r square sinus theta d theta d phi. Okay, and here too I will give you the bottom line. The mean power is the following: 4/3 of mu 0 p cube c0 p0 square f4. Okay, so the important thing is that this is called Rayleigh diffusion. Okay, and the important thing, which I will write in words, is that the mean power radiated by a dipole, okay, vibrating or oscillating dipole, okay, is proportional to the force. This is very, very important. The force power of the frequency of the dipole. Okay, and this is answering why the sky is blue. I will explain it in a second. So what happens is that the sun is actually heating the atmosphere, okay? Sun heats the atmosphere, okay? And this leads to the excitation of molecules in the atmosphere, okay? Which starts, this molecule, they start acting as oscillating dipole, okay? Start oscillating, okay? And then the moment they start oscillating, they radiate energy in all directions. And this is why you see light from the sky, not only when looking directly at the sun, okay? You actually see light from every direction. Why? Because all these small dipoles have been excited in the atmosphere and they emit in all directions. This is not the case in space, right? In space, you don't have anything there is dust, but you don't have any atmospherical molecules to excite, right? And this is why you don't see light from everywhere. So this is why, so they emit in all directions, not, well, in all direction except in the direction of the dipole, but they are oriented in many directions, so they emit technically in all directions. This is why we see light emitted from all directions in the sky, okay? Not the case in space. Okay, now what happens is that when they diffuse energy, they diffuse with this law that the power is proportional to the force power of the frequency. Okay, so the blue frequency, let's see, is about 640 terahertz. Okay, and the red frequency is about 400 terahertz. Okay, so there is about a factor of F blue is about 1.6 F red. Okay, and so the difference in power, the power emitted in blue is about 1.6 to the 4. Okay, so this is 6.5 times the power emitted in red. Okay, and this is actually our eye is sensitive to the power, to the mean power. Okay, so this is the explanation why we see a blue sky, because these molecules, when they vibrate, they emit 1.6 to the 4 times more power, more energy, which is what our eye is able to detect in blue frequencies than in red frequencies. Okay, and this is also the reason why when you look in the direction of the sun at sunset, it actually looks redder, because it's more, it's actually more reduced in the blue frequencies. There is more air. Okay, this is a slightly different phenomenon, but the same in essence. Okay, there are more layers of air when you look at the grazing orientation. And so the light from the sun is more subtracted in blue frequencies. Okay, but this is why we see a blue sky. Okay, and with this, we will finish this lecture and also the course. The exam will include everything, including what we did today. Okay, because what we did in this course is a bit less than what we usually. So the exam will cover all everything we did until today. And good luck for the exam. It was nice to teach you. And have a good summer. If you don't have questions.
Thank you. First of all, I have a question.
Okay, so let's just say that whoever wants to leave is welcome to leave and go have a good summer. Yes, יובל?
רק עניין טכני לגבי המבחן, הדף נוסחאות שבמודל זה מה שנקבל?
כן, אני אבדוק את זה שוב עם המתרגלים, אבל בעיקרון כן.
בסדר גמור, תודה רבה.
תודה לכם.
תודה רבה.
תודה רבה.
ביי.
תודה רבה.